Okay, so I think we start. Hello everyone, my name is Mikołaj Buchwald and I am a PhD student at the Atomic University in Poznań, and for like 3 months now I also work at the Poznań Supercomputing and Networking Center. But today I will tell you what I was doing for my master's thesis, and it was analyzing functional neuroimaging magnetic resonance data with some machine learning algorithms in Python. So, some overview of my presentation. First, I will tell you something more about neuroimaging, because it's not every one of you may be familiarized with it. Then, I will tell you how this data, how the fMRI data were used to and still are analyzed in more conventional, canonical ways. Then multivoxel pattern analysis, which is newer, relatively newer way of approaching the data. The analysis is based on machine learning algorithms. I will tell you how I use Python for this analysis and present you with my work actually, which is a real work almost, because it's scientific work, it's not that much real. And then some future directions and conclusions. But first, let me tell you why am I doing this? Why we are studying human beings. For generations, for ages, the greatest thinkers and philosophers and psychologists just ask what the human being actually is and how does it work. How is it possible that this trillions, billions of cells, our organism, is able to produce this, was able to come up with civilization, with this newest technologies, with language? How is it possible that we are able to walk, able to talk, and program even? And I will tell you about this metaphor, which is pretty common to tell how the study of human beings were approached. In the 20th and the 19th century, until this time, there was this behavioral theories which claimed that only the input to our labels, to our man is, and the output generated by us is important. So the inputs were like stimuli, like some visual, auditory, or tactile stimuli, and the output was like speech or some motor output, the things that we do in our life. But in 1950s, the new trend emerged with this cognitive science. It's called cognitive science, and it focused on the processes taking place in our organism. So, from our organs, the brain is the most important one in terms of those processes. Of course, there are some theories that claim that whole body is entangled in this process of cognition, but the brain is the central processing unit of our organism. That's why the cognitive science focuses on the brain. And now, how we may learn something about living human organisms. There is always this possibility that when the person dies, we can cut him or her open, we can look at his/her brain, we can check some neuroanatomical structures, and this is of course some way, but we are more interested in living organisms. So the processes taking place in working brain. There were developed some, in the 20th century, there were developed some methods to actually analyze these processes. Of both this functional magnetic resonance imaging that I will be telling about about you today. There is also computerized tomography, which is cheaper, more commonly used in hospitals, for example. There is positron emission tomography, where some radioactive markers are injected. Electroencephalography, which is still commonly used for diagnostic and scientific purposes. Magnetoencephalography, that is a bigger EEG, more complicated, also much more cost is required to perform these studies. And the newest functional near-infrared spectroscopy, which is some trade-off between the EEG and fMRI. So today, as I said, I will tell you about the fMRI and ways of analyzing the data, but I am interested in electroencephalography, but today is not the subject of today. So basically, the theory behind this fMRI is that there are two types of red blood cells in our blood, our organism, and one is the blood cell that carries the oxygen, which is called oxyhemoglobin, and the oxyhemoglobin is the red cell, which is without this oxygen already. And these two entities have different magnetic properties on the molecular level, and it helps us to, we can utilize this property to actually measure the brain signals with, for example, MRI scanner. And now there on the right there are ventricles, and in the resting normal state, as we sit or nothing in some ventricle in our brain, the ratio between the oxygenated and deoxygenated blood is quite equal. Yes, but when, for example, I'm producing speech right now, there is a brain area called Broca area, which is greatly responsible for the speech production. And now my brain is using much more resources. Resources are required to calculate the information, to convey it to you, so that there is much more deoxygenated blood than the oxygenated. And it follows like that the brain activity, it is assumed that this oxygen consumption is somehow connected to brain activity. It's complicated, and we cannot really tell whether there are some processing going on or some inhibitory processes. But generally, there is something going on in the brain. There is the assumption, and we can acquire this with scanners like that. It is obviously not for human purpose. It's to conduct some physical experiments or some experiments on, for example, small animals, small mammals like rats or birds. And in the 1990s, Ogawa and his collaborators came up with the method to measure this. So they had this theory, and they thought that it is possible. They actually tested it. They put rat inside the scanner, and they showed they were able to obtain these brain images, brain scans, which was pretty amazing at that time. And also the so-called temporal resolution was quite striking, because the time to acquire one single scan of this brain, it was possible to do it in like 2 seconds or 4, whereas previously used method for neuroimaging like this PET, its temporal resolution was like minutes, or 10 minutes, or 50 up to 30 minutes. So now we were able to see some processes going on almost in real time. 2 seconds are not that real time for our brain, but it's much better. And nowadays there are scanners like that in hospitals or in some research facilities. There's this table when our patient or our participant is put. It goes into the scanner. There is coil used to, based on these differences in magnetic properties, between the oxygenated and deoxygenated blood, we are able to transmit this signal and obtain images like that. So on the left, you have classic MRI images. You may be familiar with it because, as I said, it is used for diagnostic purposes, to diagnose, for example, Alzheimer's disease, or to see what is going on after some traffic accident, yes, whether it is stroke or stuff like that. It is pretty useful, as you can see. And on the right, you have some much lower resolution, bold fMRI contrast, which we can use to see how our brain is working in real time. Okay, so here I have some example image for you. It's quite dark. We may do something about it. Now you can see that this tissue is quite healthy. Yes, we have some frontal, some occipital lobes, corpus callosum here, and some other brain structures like ventricles. And it's pretty healthy brain. If it had like some deterioration, you could see the black patches here. Some tissue would be missing, and this brain is quite good. And as you can see, it's like 3D picture actually of our brain. So this kind of goes like slice after slice, or even odd slices, and we obtain image like that. And how does it differ from the bold fMRI? I can show you some MRI now. And as you can see, the picture is much worse quality because the contrast is here is more demanding computationally for the scanner, and as the MRI image is acquired for like 10 minutes or 15, this has to be acquired in 2 seconds. So obviously there is some trade-off of we lose some spatial quality. But nevertheless, as you may see here, on the voxel location, because the voxel is one 3D pixel actually, yes? So as you can see, this array here is quite big. So if you calculate this 40 per 40 per 60, you get quite a big number, and additionally there is also volume. So I can show you like movie. I don't know if you can see it, but there is something going on. Like here you have the signal changes, but the change within this signal is like 2 or 3%. So if anyone could actually see what is going on there, I would be pretty surprised. And to get some meaningful output from this, we need some complicated and heavy statistics and particular ways of analyzing it to get some interpretable data out of it. And I will tell you about those methods in a minute. Okay, how this fMRI experiment looks like. You present your subjects, your participants with stimuli, like for example, as A, you present for 10 seconds colorful pictures of some objects, then grayscale pictures, so everything except the color is the same. Then you repeat this for like a couple times for each subject, for a couple of runs. Between runs the subject may rest for some time. Then you average the whole B condition versus A. It would be like here would be colorful minus grayscale. You get some contrast, you threshold it with some given probability, and you obtain images like that. But as you may imagine, not every process that are taking place with us, with our organism, is so spanned, like for 10 seconds. There are some actions like, for example, reaction to some frightening stimuli, or like me grasping this bottle right now. It doesn't happen for like 2 seconds or 10, but it's almost instantaneous. So how do we deal with this when we have only 2 second scan? We may, based on the theory that we have, on the electrophysiological studies, we know how these neural cells should react for our action. So there is like function that describes it. We model our data, and with this a priori ideal model, we gather the data from the brain. We do this fitting with general linear model for all the voxels within our brain, and for those voxels where the errors are the lowest, so the fit is the best, we assume that there in the brain the process is actually going. And to compare the conditions, we can get those fitted beta values for one condition. For example, as we had with colorful pictures, we subtract from it the grayscale, we divide it by combined error, and we obtain maps like that. So it's pretty straightforward anyway. And then in 2001, new approach emerges where we are not contrasting. We are not just contrasting one condition with another, but what was done here, the Huxley and his collaborators, they came up with idea that they showed the faces, the pictures of faces or pictures of houses to their participants, and then they had like even and odd runs. Yes, so there was like 10 minutes of scanning, some break, another 10 minutes. They took the even runs and they correlated the data with the odd ones. So what they obtained was the pretty high correlation between the faces stimuli, but when they correlated it with responses for houses, the correlation was reversed, and for houses it was similar. So what they basically were able to do, that they predicted, based on, for example, even runs, they predicted what the person was doing in the odd runs. Whether the person was looking at the houses or faces. And it is pretty amazing, because it was done only based on the signal from our brain. Yes, this one step from that to decoding, for example, whether I'm willing to use my left hand or right hand, or maybe even to detect which person is lying, or whether it's he or she is telling the truth. But this level of abstraction was not achieved yet, but you get the idea. And then after a couple of years, the increasing trend for machine learning and artificial intelligence allowed us to not only detect, to not only use the correlational methods, but also some artificial intelligence machine learning, where, for example, on runs 1 or 2, the classifier was trained, and in the third run, we tried, or they, Norman and collaborators, they tried to distinguish, for example, this bottle from shoe, whether the person was looking at the bottle or shoe. So the time needed to accurately predict what the person is doing decreased with these algorithms. What are the difficulties with this multivoxel pattern analysis? In the block design that I told you about, this 10 seconds, 10 seconds, 10 seconds, you take like this 2-second scan and you feed the data, feed this input in your classifier. It's pretty straightforward. But for the event related, you cannot do like that, because some events may overlap over, for example, 2 volumes or 2 scans of the brain. So what you have to do, you have to extract somehow this information. It is done by modeling the information, very similar to the subtraction that I showed you. But you don't subtract the signal, but you are you give this data weights to your classifier, and you are able to predict in particular trial whether the person was, like, for example, grasping bottles or doing nothing, or like waving hand. So the lower approach, the methods within the MVPA itself is like region of interest, where you take the particular brain, not the whole brain itself, because it's pretty expensive computationally to do it, and sometimes you're more interested in particular area than the whole brain. But you also can use the searchlight method, where there's this span of light, this spherical area of interest shifts all over the brain with its central voxel, and then you acquire the whole brain maps very similar to the contrast. But it informs you about something else. It informs you in which areas the signal is processed, which areas are the best to decode this information. And to go to the software, there are some ready-to-use packages for analyzing fMRI data, but there are some disadvantages of these packages, because they both have both like graphical user interface as well as some, for example, bash commands. Yes, but if you're willing to analyze data from like one participant or 2 or 3, it is possible to use it. But if you have like 10 or 20 or 40 or 100, 200, 1,000 participants, it becomes more and more difficult to deal with this data. And obviously those packages still lack some functionalities that may be provided with some lower level software like Python or MATLAB. Both technologies are quite popular in the scientific community, but the Python has some obvious advantages over MATLAB, like it's open source, it's free, it has strong, growing, thriving community. You can see here, I'm sitting and discussing issues with this language, and MATLAB is like MATLAB. Not fun, the whole this software. Okay, so there is this initiative called nipy, which gathers all the software related to neuroimaging data analysis. As you can see, there are several such packages, and today I will briefly tell you about those that are used. Nipy, which is basically interface for the packages that I showed you before. And with these interfaces, you are able to show you. You are able in easy way to prepare this workflow, to change some parameters that are used, like for filtration, like which images you are using, etc., and some smoothing, and then you get this pretty complicated graph. But what it basically do is that you put your data in the input, and after all analysis you obtain some meaningful output. Yes, and you can easily automatize this to analyze data for like tens or hundreds of samples. It's harder to learn it than to use these graphical interfaces, but it gives you more power and some advantages. And also what it allows you to do is to combine this, like for example, as FSL with preserve. So normally you would use like bash, or you just like use the data to analyze one file, then open another program and analyze it, and with Python you're able to prepare the workflow, run it, and like go 2 days later and you have everything out. Then you have nibabel, which is lower level. With this package allows you to manipulate the data. So you can load the neuroimaging data, because this data is usually not stored in some pretty databases like Postgres or MariaDB, but those are rather so-called nifty files, special format. And what it is basically some like header that informs you how, with what parameters this data was acquired, and then you have like 4D array where the data are stored. So there is X, Y, Z axis and like time. So if there were like 150 volumes per 2 seconds, this 300 seconds of scanning, it would be 150 here. And with nibabel we were able to load this image to get some mean or standard deviation, stuff like that. Maybe I will show you. Takes some time, but finally we have number. We can calculate the mean, standard deviation, stuff like that. We can operate with it in some shape, some further way. Okay. It's actually, yeah, it's not the 150, but it's like 6 runs or more combined. So there's like half an hour scanning. Okay, and with this nibabel we can also perform some basic visualization. Although there are more complicated software, there's more complicated software to do this. Then we have nilearn, which is based on scikit-learn, and this package allows us to easily load our neuroimaging data and perform some analysis, some MVPA analysis. And after this loading data, defining what was the target, what the person was doing in the scanner, we can perform analysis, and there is an example where you have some different ROIs, this is region of interest. It is like ventral, which is responsible for perception, for image processing, and some parts of it is like face specialized area and house specialized area. And here you can see, like, for example, that for mask house, you have like very high accuracy of the coding in the house, but not in the face. And in the face, you have like almost 90%, while for houses, this mask face gives only like 70%. And some another example, you go to compare faces with houses, and you want to check which algorithm is actually the best to distinguish those two brain sets. So you have like SVC, SVM is pretty decent, gives pretty decent results. The KNN is much worse, and the LDA is pretty similar to LDA. And now my example that I promised at the beginning. There is this brain network called Praxis Representation Network, and it is responsible for like very well trained gestures, or supplying of these gestures, like grasping objects. This generally some more complicated stuff we do with our hands. Yes, so like waving, non-verbal communication, and this network is mainly lateralized. And it consists of like supramarginal gyrus, caudal-middle temporal, premotor ventral, dorsal, and middle frontal gyrus. And there was the study in my laboratory when where my supervisor and one of my colleagues wanted to check whether this network was previously associated with actually using, for example, a tool. Yes, and they wanted to check what is going on in the brain before the person actually moves the hand to grasp the object. And they discovered that even though the action is not yet being performed, this network is like active. So it calculates very, very much data before the movement itself, and then it's gradually decreasing. Previously, this planning phase and this action phase was not dissociated. And they used this paradigm and they presented some pictures like tools which have some particular function and some non-tool branches or wooden sticks, and they asked participants to imitate the grass, because there were no real objects, because it's pretty hard to get some real world objects in MRI scanner, because it cannot be like metal, it has to be plastic or wood. Now we perform some analysis, some experiment like that, but then in 2015-16 when they performed it, they had like only pictures, and then people were asked to lie in the scanner, just imitate the grass. So it was either that or this way for tools or non-tool objects. And what I did for my master's thesis was that I took some sub-regions of this per-axis representation network. Those are regions in the left hemisphere. And using the softwares FSL and Python, maybe I'll tell something more about this, because I used this nilearn, scikit-learn, but the part for group analysis I had to implement largely myself, because the nipy was not yet operational at that moment, and it took me some time, and I will not show you the code today, but it was pretty demanding for me to learn how to do this. And then I obtained this pretty nice graphs with this nilearn, and slightly modified it with matplotlib. And as you can see, this region, those regions like premotor dorsal cortex is pretty good for distinguishing between the tool and non-tool object, while, for example, this control region with this right lateral ventricle, where there is there shouldn't be any meaningful signal, but due to not perfect registration algorithm, there is still some classification there. But the results that I obtained are statistically significant with respect to the chance level, when I would like to just guess by randomly choosing one or two class, and with this control compared to the control region, there is also some significance. And I also performed the searchlight analysis, and after that I thresholded the results, and I obtained maps like that I mapped to the blood and fiducial brain models, and these maps that I obtained for either the left or the right. The participants were asked to do this grasping either right or left. And there are some inferences. There is my supervisor and colleague from my lab, whose data I used to perform this analysis. And hopefully I think that with these new technologies, with new software, better, bigger scanners, maybe there is a chance that we better understand how does our brain work, and generally what makes us human, with some research. So thank you for your attention, and you can contact me if you have any further questions or insights. I will be grateful for them. Thank you. Okay, we have some questions. After we learned how one person's brain reacts to different objects, bottle or shoe, how accurate the predictions would be for other people's brain. Yes, this very important question, and actually the same group, this Norman Huxley that I showed you, they in 2014 they used very complicated registration algorithms, because the main issue here is that each and every one of us have different brains. Yes, generally there are some structures like frontal lobe or like occipital, parietal lobes, but if you look like for brain from one person and from another, there are many differences. Yes, and the difficulty here is to match one brain with another. And to answer this question directly, I would say that it wouldn't be pretty successful with the standard algorithms. If we were using some cutting-edge stuff, like not available only for a few people on the world, in means of understanding how does it work, it would be possible. But for now, the research is performed like only within subjects, and then averaged and so at some higher level. Okay. Are there any areas of fMRI analysis where human analysis is better or more reliable than computer and ML analysis? Yes, there are some areas where, for example, for the brain segmentation, yes, where we are looking at the brain, our brain is much better still at differentiating between particular gyri and sulci than the machine learning algorithm, although there is growing research in this area, and the algorithms are getting even better. And also maybe it's not strictly fMRI, but in MRI, the diagnosis performed by medical doctors is still considered better when it's performed by human being. But there is even less difference between the human and algorithm results. Okay. Are there any public databases for example, fMRI results? Of course there are, because this neuroimaging society, this community is very open, and there are initiatives like Open fMRI, where you can see some data. Maybe I will use we have still some time. Okay, there are basically, I think, three main initiatives. One is this Open fMRI. One is Open fMRI, another is called Nitric, where the neuroimaging data as well as software is being distributed, generally for free. Sometimes you have to register and say, I am a PhD student, I'm a researcher, I'm some medical doctor, medical facility, give me this data. And they usually validate your credentials and they show you this data. Okay, there is one more initiative which is called Human Connectome Project. There is this huge project sponsored by by US government, and they also can share with you data. They have like 1,000 people scanned with 7 different paradigms, 7 different cognitive tasks, also some structural data, and most of those participants are twins. So they have also like genetic data. So yes, there is data available, and if you just like type in your browser Open fMRI free data sets, you can download it. It is pretty good. There are descriptions what the people were doing while being scanned, And okay, maybe next question. And meantime, I'll try to open the. And is it common to use machine learning algorithms to find diseases from cheaper medical tests? Maybe like blood tests. I don't know if I understand this question correctly, but there are some algorithms to detect like schizophrenia or Alzheimer's disease. Also, there is research about this heart activity, so ECG, and it's medical tests. The problem with using machine learning algorithms for medical purposes is that it's not that openly embraced by the medical community. So I will not comment further on this, but okay. You have like OpenFMRI, where you can view data sets, submit your own results. There is also neural code. It's majorly for results, not the data itself. Okay, and maybe I'll show you this human connector, because it's a project that makes impression. Okay, it's like that, because there is one more way to visualize the MRI scanner. It's called DTI, this is diffusion tensor imaging, which allows you to trace the neural pathways in the brain. Yes, so they show quick images like that, and it can be very informative. How advanced hardware is needed to effectively use the software you showed? Can it really be scalable? Yes and no. Because this software is created mostly for some individual researchers, and the need for example, high computing performance is not that big within this research. There are projects, more complicated projects like the one that I show you here, but they build their own software to scale this analysis for like this 1,000 people to perform it very fast. There are also some neurobiological studies where they are simulating like cortical column from the rat's brain. They trace almost exactly the cells as they are positioned in the real rat brain, and they try to simulate processes. And for that, there are also different software that is better scalable than things there. The one advantage of nilearn, for example, is that you can parallel this analysis, for example, for 4 cores that you have. That's all about this. That works. Scalability. To what extent is the limited resolution is fit into sphere? There are 2 types of resolution. Yes, there is this temporal resolution, where the scanning takes place for like 2 seconds. And for example, for EEG, the temporal resolution is like 510 Hertz or like 2056. So you can compare that here. It's almost instantaneous, while fMRI takes some time. But there is always this trade-off, because in EEG you have like only 20 or 60 electrodes or 120, and there is only from those places you can acquire the data very quickly, but only from the scalp, and using fMRI or NIRS, you can get into the brain, and you get like tens of thousands of places in space. So this resolution concerning how many places you can measure is much better. I want to start learning ML, where I should start with and what skills should I have to be good? Maybe I can tell you my story, because I was studying cognitive science, and also I'm PhD student of the cognitive science, which is in Poznań. It's at the Institute of Psychology on the social sciences faculty. So I have basically no formal background, formal programming background, like from technical university or from some mathematics or informatics faculty. But I took some courses. I used this individual study program where you can choose some courses from different faculties. Yes, it's one way to do this. Where if you are still studying, the universities now are pretty elastic, and you can adjust your program to what you are trying to do. If you are not willing to use this formal education, you can always go to like scikit-learn page. They have some pretty decent like tutorials and examples. At least for me, it was easy to learn from that. Will we be able to read human hopes in the future? Do you think it is real? This is more of a question, it's more philosophical question actually than technical, because depending on the assumption, if you assume that our brain, our organism is just composed of cells, of neural cells, and everything can be reduced to these few electrical or chemical processes taking place in our brain, it is obviously possible to read thoughts. It's a matter of maybe tens or maybe hundreds of years, but at some point it would be possible. Of course, the research is going on about this telling true or lying. There are some labs in Philadelphia, I think, that they are trying to predict whether the person is telling the truth or there is something not right with his or her statements. But on the other hand, if you're like deeply believe person and you think that there is some psychological aspects of our existence that cannot be reduced, then the answer is negative. So we never would be really able to understand what is going on there, to read thoughts, to maybe suppress some memories or inject new ones. But it really depends on what do you believe in. Something about reading human thoughts, the ex-neuron, the lustrzane. Lustrzane mirror neurons are very tempting and very, used to be and maybe still are very we want to believe in mirror neurons. For those of you who don't know what it is like when they were performing electrophysiological studies in Parma University in Rizolati's laboratory. They had like monkey, macaque I think it was, and it had like needles stuck in its brain, and the parietal cortex, and the researcher there then dropped something by accident, yes, on the floor, and he like tried to grasp it. And at that particular moment, they observed the strike in this neural activity within this around this needle. And surprisingly, it was active only when someone else, like another monkey or person, was doing something, like was trying to grasp. Yes, and it was called mirror neurons. The popular science, I would call it. Maybe it's a very big deal, but actually it was more like, at the beginning, it was more like just the theory, and its intention weren't to reduce everything to, like, this neuron is responsible for social cognition, this neuron is responsible for grasping. It's not that easy in the brain. So the mirror neurons are very interesting, but we have to be cautious. Approach to this with caution. Do we all have the same image when looking at the same thing? Again, yes and no. Because theoretically, we should have the same brain image when looking at this thing. But there are these so-called confounding variables. So when this one person is in the scanner, it's he or she is more tired, or he's also thinking about something else at that time. So the other neural activity is covering what we should see as plain image of, for example, house. And also there is this neuroanatomical differences that I mentioned to you about earlier. Yes, so we should have, and at some stage we have the same image, but it is covered by some other conditions, some other variables that we are not able yet to control during our experiments. There have been issues recently with medical imaging analysis systems using inappropriate features. How would you propose me making this? I think that you refer to this bug that was recently, last year or 2 years ago, was discovered. It was a bug in the software. If it's not the answer to this question, it's nevertheless interesting. This software that I showed you, those packages are basically built one up. They sometimes use the same ground software, yes? So this higher level of abstraction, but beneath this is, for example, like AFNI package, which all three of those use, and in the source there was some bug. And they fixed it, they found it after some time, and it is not the issue now. Hopefully there are no other bugs there. What about the scanning of animal brains? Is it? Of course it is. As I showed you, the first experiments were performed with rats, or there are some dog studies now pretty popular. Like, for example, they are showing dogs, the dogs are trained to sit still in the scanner, because every movement there is another confounding variable. But they take images of dog's brain while the dog is watching, for example, other dogs' facial expressions, or people, and they are trying to check whether the dogs can distinguish emotions of conspecifics or from humans. But animals are always before human trials, and sometimes it is also interesting to see whether, for example, the rat has some similar brain function to us. It would mean that it originated somewhere lower in the evolutionary tree. So it's interesting to study this. Is high resolution of fMRI weekly well, or actual arguments are good enough to work with what you have? There is always growing need for higher resolution, some higher temporal resolution, for example, but there are some technological, physical difficulties with this. Because, for example, at the beginning, the scanners for human trials, and still very popular, are 1.5 Tesla. So the Tesla is the measure of magnetic field. We used also the 3D Tesla scanners. There are 70, not only for animal studies, but also for humans. But the difficulty there is that it's very sensitive. Yes, so like every little movement gets you some distortion in the data, and additionally, the magnetic field is that strong may induce some muscle contraction. Yes, so like the legs are moving without the person's willingness to move. It's pretty scary. And it's difficult. While the temporal resolution, the temporal, not the temporal resolution, the acquiring even faster would be very needed, and it needs, for example, address this question. It gets you data much quicker, almost like the EEG, but you have information about the blood flow within your brain. Have you considered feeding 3D images to 3D CNN instead of extracting activity levels from specific areas of brain and using conventional ML. Of course, I tried to use these CNN networks, but the difficulty here for me was that, presentation. Yeah. For my master's thesis, I performed many analyses with different algorithms, different setup, etc. I also used CNN networks, but the difficulty here for me was that I had like very few data points, because there's 2 seconds only, and each person has like, let's have it, 1,400 points, but it's still not enough for this deep learning or convolutional neural networks to learn, to get some insights from it. I have seen studies that use like thousands of medical scans and structural, for example, and they also extracted some features from this, and it gave them opportunity to really train this network and make it work. But for me, it was easier to use. It was better to use like SVM or something that does not require that much data to feed at the beginning. The FDA are planning to regulate algorithms as medical devices. Your thoughts on this? I think it is a very good idea, because as I mentioned, the medical community is very cautious about this introducing algorithm, not the where issue to calculate, to decide whether the person is sick or not, because it has many ethical implications, and if there were some standards about how to use these algorithms and who's responsible, for example, when the algorithm says that the person is perfectly healthy and he or she dies like a week later. There are these difficulties, but I think that the work there is needed, because algorithms are getting smarter and smarter, and on the greater scale, it will be better than humans. So why do we not use algorithms to help people, to diagnose them, while we have this opportunity? Yes? Then we actually harm the people when we are using only the human brain power to try to help them. Very complicated ethical. Have you done any experiments with mental disorders using machine learning? Yes, I did. I actually downloaded one of the databases. I downloaded schizophrenia data. We are after time, but I think that if you're willing to listen to those answers, you can still wait. I basically, with my student research group, we downloaded the schizophrenia data and we tried to analyze it, but having not so much experience with anatomical and resting state, because those were discounted. The people with schizophrenia or controls were not actually doing any tasks, but they are lying in the scanner. There's this paradigm is called resting state with eyes open or closed. We had some results that were showing that, for example, the precuneus was maybe partly responsible for the schizophrenia, but the literature there about schizophrenia or depression is very diverse, and we cannot have like we cannot be for sure to how to do it. If any one of you is interested in this more medical stuff, this is from Nietzsche, you can download like schizophrenia, depression, mild cognitive deficit, Alzheimer's, and stuff like that. This page is so the questions disappeared, so I guess there is time for us, and I'm once again very grateful that you